At 7:05 on a Friday evening, hundreds of people filled the atrium of the Hyatt Regency Hotel in Kansas City. A band was playing. Couples were dancing. Guests leaned against railings on suspended walkways above the lobby, watching the crowd below. Then came a sharp crack. The fourth-floor walkway dropped. Because a second-floor walkway hung directly beneath it, both bridges fell together onto the packed dance floor. Steel, concrete, and glass crashed through the atrium in seconds. 114 people were killed, and more than 200 were injured. The disaster looked sudden. The engineering failure was not. The hotel had opened only 1 year earlier. Its dramatic atrium contained 3 elevated walkways suspended from the roof by steel hanger rods. 2 of those walkways were stacked vertically. The arrangement looked elegant and modern, but one connection carried a hidden weakness. To understand it, imagine a long steel rod hanging from the ceiling. In the original concept, that single rod passed through the upper walkway and continued down to support the lower walkway. Each bridge had its own nut beneath it. The load from the lower bridge traveled directly up the rod to the roof. That design was difficult to fabricate. A single threaded rod would have to pass through the upper bridge while still allowing its nuts to be installed. The steel fabricator proposed a change. Instead of one continuous rod, the revised design used 2 shorter rods. One connected the roof to the fourth-floor walkway. A second rod hung the lower walkway from the upper one. The change looked small on a shop drawing. Structurally, it was enormous. Under the revised arrangement, the connection at the fourth-floor walkway no longer carried only the weight of that bridge. It also carried the entire second-floor walkway hanging beneath it. The load on a critical connection was effectively doubled. According to the American Society of Civil Engineers, the revised connection could withstand only about 30% of the required minimum load. Even the original concept failed to satisfy the applicable building code requirement, but the approved change made the weakness far worse. This was not simply a bad calculation. It was a failure of responsibility moving through an entire chain. The fabricator requested the change. The engineer approved it verbally, expecting a written request to follow. That formal request never arrived. Shop drawings were prepared under schedule pressure. Reviewers assumed that someone else had already checked the connection. The drawings were stamped, but the critical calculation was not performed. Every person saw only one small part of the process. No one stopped to verify what the complete structure would now be forced to carry. There had already been another warning. During construction, part of the atrium roof collapsed. Investigators later found no direct connection between that roof failure and the walkway design, but the incident should have triggered an unusually careful structural review. Instead, the hotel moved toward completion. On July 17, 1981, roughly 1,600 people attended a tea dance in the atrium. The suspended bridges became viewing platforms. Dozens of guests stood on the second and fourth floor walkways. The walkways were not overloaded by an impossible crowd. The connection was simply far weaker than a public structure was required to be. As people shifted and danced, the box beam connection around one of the hanger rods began to deform. The nut supporting the bridge pulled against welded steel channels. The channels bent inward. Once the connection failed at one point, the load shifted violently to the remaining supports. The fourth-floor bridge fell several meters onto the second-floor bridge, and both crashed into the lobby. The impact destroyed water pipes and filled the rescue area with flooding water. Survivors were trapped beneath slabs of concrete and twisted steel. Emergency crews used jacks, cranes, saws, and improvised supports while doctors treated victims inside the ruined hotel. The rescue continued through the night. The National Bureau of Standards, now known as NIST, examined the wreckage and tested the failed connections. Its investigation concluded that the collapse most probably began at a box beam and hanger rod connection on the fourth-floor walkway. The physical distortion matched the weakness created by the revised design. The legal and professional consequences were severe. Engineers connected to the project lost their licenses. The disaster became one of the most important ethics cases taught in engineering schools. But the lesson is larger than one drawing or one engineer. Modern buildings are created by networks of architects, engineers, fabricators, contractors, inspectors, and owners. That complexity can improve safety, but it also creates gaps where everyone believes someone else is responsible. A shop drawing is not a minor administrative document when it changes how a structure carries weight. A signature is not a substitute for a calculation. And schedule pressure does not reduce the force of gravity. The Hyatt walkways did not collapse because engineering was incapable of understanding the problem. The mathematics was straightforward. The failure occurred because the calculation was never completed at the moment it mattered. Today, the disaster is remembered whenever engineers discuss design review, communication, and the duty to protect the public. The failed connection was small enough to fit on a desk. Its consequences filled an entire atrium. Before the steel broke, the process had already failed. The warning was there, hidden inside a change that almost everyone assumed someone else had checked.